we just learned is that within the square, this whole square, its area should be exactly equal to the area of all the colored parts. Let me just rewind this animation, go back to the original figure. So in terms of A, B, and C, we want to know what are the areas of the two shaded square and the large square from side C. The large square from side C, that's pretty easy. That's equal to C squared. What's the area of the two squares? Well, this one has side B, so it's B squared. This one has side A, so it's A squared. What are the area of the two parallelograms? It has nothing to do with side A. We're going to use this segment right here as the base. And that base segment is equal to this side, which is B, okay? And then multiplied times the height. The height's not even showed up here, so there it is. It's this height, B times H, and we have two of them. So we're going to write an equation that expresses that relationship, that the region 1, area of that big square, is equal to region 2, the area of all the colored bits. So region 1, that's C squared. That should be equal to A squared plus B squared plus these two parallelograms, 2BH. Problem here is that this H has nothing to do with this triangle, the original triangle that we would be given. So we need to get rid of it. We need to substitute it with something else. Okay, so notice that the height in this parallelogram, it makes a right triangle. So we can use trigonometry in order to find that height. Just need an angle measurement. So we'll call this angle formed by side A and the height, call that theta. So what ratio would we use in order to find the height? Well, this is the adjacent side. That's the hypotenuse. I believe that would be cosine. Law of cosines. Okay. So if we're going to write ourselves an equation to come up with the height, it would be the cosine of that angle equals the adjacent, which is h, over a, and then solve it for h by just multiplying the a over. Now there's another problem. The other problem is the fact that there is this angle theta that's in there. It has nothing to do with this triangle again. Okay, so notice that it makes a linear pair with angle C that is inside of the triangle. Linear pairs add up to 180 degrees, so there's an equation that relates theta to C, and that is theta equals 180 minus C, because they're supplementary. So now we substitute that in for this angle theta here, and we don't have any problems anymore. All right, one last substitution. I'm going to take that, put it in for the height into that original equation that we came up with. So it looks like this. This is the law of cosines. However, this 180 minus c, you don't usually see it that way. We're going to use one trig identity in order to simplify it. And that is cosine of 180 minus theta is equal to negative cosine of the actual angle theta. This is a trig identity you'll get in pre-cal, and you'll have to probably prove it at some point. So we're going to use that, substitute that in here, and notice that what that's going to do is it's going to change this sign from a plus sign to a minus sign, and there is the law of cosines. So remember what we discussed was that you have to add or subtract something from a squared plus b squared equals c squared in order to make the equation balance. So if c is an angle in between 0 and 90 degrees, if it's acute, then this whole thing is positive, and I'm subtracting a positive number from a squared plus b squared, and that'll make it equal to c squared. If it is an obtuse angle, then the cosine of an obtuse angle is negative. When I subtract a negative, it makes it positive. It's as if I'm adding something to a squared plus b squared to make it equal to c squared. And there you have the law of cosines.